introduce Parham Salehyan from UNESP, and he will talk about on a criterion characterizing Grassmann Cones.
Okay, first of all, I would like to thank the organizers and also the staff of IMPA. Thank you very much for being here again. Today, the focus of this work, it's a joint work with Letterio Gatto, is to write the equations characterizing the Grassmann cone, that is the composable elements of a finite exterior power. That is the image of this following map, natural map that we can define between the Cartesian product of a Q vector space and the wedge of M. First of all, I would like to introduce some notations and preliminaries. M always stands for a Q vector space of infinite countable dimension. Let's consider a basis for M given by B. And we will denote the restrict dual of M, that is M star, by M star, that is a vector space whose basis is beta A, defining in this natural way. Also, PR denotes the set of the partitions of lengths at most R. And given a basis for M, we can get a basis for wedge Rm defining in the following way. That is, in fact, parameterized by the partitions of lengths exactly R. Another notation that we use during this talk is the notion of contraction, a vector of M star, that is the restricted dual, by an element, the restricted dual of M. That is given beta of M star and an element of wedge R of M. The contraction of M against beta is the unique element of wedge R minus 1 that satisfies this equation. For example, over M, we have this description of the contraction, and over wedge 2, we have this description. We will also define a sequence of endomorphisms of M, denoted by sigma I, that is nothing more than shift endomorphisms, defining over M. And we consider the formal power series sigma I ZA, which is an element of this ring. It can be extended uniquely to an algebra homomorphism from the whole exterior algebra of M. It's a straightforward demonstration. Just you can define a map from the tensor product of M, and after that, using the universal property of the exterior algebra, extend it to wedge M. This algebra homomorphism satisfies this equation, this equality over M. And we also denote its coefficients by sigma I again. As sigma 0, by definition here, is the identity map over the exterior power, it is invertible as a formal power series, and its inverse satisfies this equation here that we also used during the proof of the main theorem. This following relation will be important for us. That is, all of the elements of the basis of wedge R can be obtained after finitely many applications of sigma i's over this special element. That is B1, wedge B2, B0, wedge B1, up to BR minus 1. In a similar way, we consider sigma minus J, that is the shift by negative index. And in the same way, we can consider this formal power series and denote its extension to to the whole exterior power by sigma minus. It is also invertible, and we have this equality here over M. And in this case, we have this relation. That is, it means that it has some fixed points. Here are some properties of these homomorphisms. In this special case, we have this equality for the coefficients of sigma plus and minus for the inverse of these homomorphisms. And we also have this equation that is, in fact, a relation between the inverse of sigma plus and the inverse of sigma minus. And this is something like that, just changing sigma minus in this side and sigma plus in this side. But it is valid only in this case, because in other cases, we have this element would be 0, but this element would not be. Also, we have this information about the transpose of this element, of this series. Just for a moment, given a homomorphism like that, in general, D from we can define the transpose of D in this way. Given by it is also a homomorphism between the algebras given by the restricted dual. And we have the following information about the coefficients of this formal power series. Now we have all of the notations that we need for announcing the principal result. In fact, it is based on a well-known criterion, that is, an element of a finite exterior power belongs to the Grassmann cone if and only if we have this condition. Notice that it's a finite sum, because the contraction of the elements of M would be 0 except for a finitely numbers of elements of the restricted dual. Now, by the definition of sigma plus, we can write this sum in the following way. And of course, in this way, it is in fact the last property that you have seen before here. And this equation can be written in an equivalent form as this condition about the residue of a formal power series. Just for a moment, it can be, if you consider these would be considered as an element of if you consider this formal power series and compute the residue of this series, you can this condition here is exactly the same one here. It's a straightforward calculation. Now in the following steps, we will write these terms of each of this equation using some properties that we have shown before. In fact, we have the following equation. Just for a moment, you have to notice that as sigma plus is invertible and it's a homomorphism of algebras, we can write any equation in fact, for obtaining this equality, first we have to use this equality here. Because sigma plus is an algebra morphism, and it's invertible as a formal power series. So, in fact, you can factor sigma plus and write just the inverse of sigma plus here. The same thing holds for this equation here, this equality. And finally, we can obtain the result. That is, an element of the exterior power, finite exterior power, is an element of the Grassmann cone if and only if this residue is 0 as an element of this tensor product. For an example, it is simple to verify that this element of wedge 2, where M has at least dimension 4, is not decomposable. And if you compute the residue, it will be this element that, of course, is not 0 because this is an element of the basis for M tensor. So, of course, it's not 0. Now, I would like to obtain a polynomial version of this criterion here that it would be much more interesting, I think, in order to use it. The polynomial version is based on the following two facts. First of all, let's denote by the polynomial ring in R determinates over Q by BR. There is a natural isomorphism between BR and wedge R of M, as I will explain in a few minutes. And there's a natural BR module structure for wedge R of M. For these facts, we first consider this polynomial. This is a special polynomial which is an element of BRZ, and construct a sequence HI of elements of BR in the following way. This is, in fact, the inverse of this polynomial that we can write in this form, and we can obtain this equality, which is an equality in this ring. That is a formal power series, and Z with a finite number of exponents. It will be Z minus 1 for a finite number of elements, terms maybe. Maybe the right notation would be this one. Anyway, by definition, the Hj for the negative indexes are 0, each 0 and 1, and for each I positive index, Hi is a homogeneous polynomial of degree I in determinants if each Ej is given weight j. And this is well known that this is a well-known result here, that BR is generated over Q by the sure determinants associated to this sequence. That is, if we denote this determinant by delta R HR for any element for any partition, we have that BR, we have this direct sum for BR. The isomorphism between BR and wedge R of M that I've told before is given by this map. That is, we get the basis of BR and maps it to the basis of wedge R of M. And the BR module structure of wedge R is defined in this way. This product, the scalar product between the elements of BR and the basis elements of wedge R is given by this notation here. Remember that sigma I bar are the coefficients of the inverse of sigma plus, as we defined it before. Accordingly, taking a sum over this, both sides of this equality. We have this equation. And taking the inverse as formal power series, we have this equality here. In particular, sigma I mean the coefficients of sigma plus applied to B lambda R is exactly this element of wedge R. That is, HI can be seen as an eigenvalue of sigma I seen as an endomorphism of wedge R of M. It is really important during the obtaining of the polynomial version of the theorem. Now, we also define these applications between BR and BR Z inverse in the following way. And in particular, we have the following information for sigma minus and sigma minus bar, the inverse of it, over BR. That is, over every Hn, sigma minus Z acts as this sum, the finite sum, and the inverse is like this. Another two important facts that are that in wedge R plus 1, we have the following equation. That is, we can write this expression as the action of this sure determinant over this element. And is in wedge R minus 1, we have the following expression. Note that we have here the contraction, so both of them are elements of wedge R minus 1. Now, coming back to the theorem, remember that an element of wedge R of M is an element of the Grassmann cone if and only if the residue of this formal power series vanishes as an element of this ring. Okay, since this element here is an element of wedge R minus 1 of M, it is an eigenvector of sigma plus R, sigma plus bar of Z, corresponding to the eigenvalue ER minus 1. And in the same way, this part from here, it's an element of wedge R plus 1, and it is an eigenvector of sigma plus Z corresponding to this eigenvalue. So we can simplify a little. Each terms of this sum in this way. This is the eigenvalue. So using these properties here, we can write each term as the following way. And finally, we can obtain this equality for each terms of the expression. For this equality, here, just note that we can identify the tensor product of these polynomial rings of R minus 1 and R plus 1 indeterminates as the polynomial ring of 2R indeterminates. This is straightforward. And as this element of this vector space is the basis element seen as a module over this polynomial ring, we get this simple expression for this for each term. So an element of the Grassmann cone, an element of the finite exterior power is an element of the Grassmann cone if and only if the residue of this expression is 0. This is the polynomial version of the theorem. But we can see this criterion in a much more simplest expression. That is, let ER prime, ER minus Z, this polynomial, which is an element of BR minus 1, and this polynomial here, let consider the inverse of these polynomials in these rings here. So the formula given here can be wrote in this in this residue form, that is, in fact, it's a calculation in the polymer rings. That is, you can do it more or less in a simple way. For an example, all the polynomials that something like that this action is an element of the Grassmann Cones satisfies this equation here. That is, it is a well-known example that, of course, we can get it again by this formula here. Okay, this is the references. You can find much more details of this work here in this article here.
Are there questions?